Hello, everybody. This is Debbie Spoons, NSS webinar. This is CaveNet. We are here for Hazel Barton's part 2 of the phenomenal webinar she gave us about a month ago on the coronavirus. We can't thank her enough for taking her time and putting these PowerPoints together in her incredibly busy schedule. Right now, I'm going to explain a little about Hazel's background, a little. She didn't give me a whole lot, and I know there's a whole lot more there, but we're going to go over what I have. Hazel has 2 PhDs, one in medical microbiology and one in immunology. She's a professor of biology and geology and has been teaching medical microbiology for over 20 years at the undergraduate and graduate level. Hazel has served for 6 years on the Public and Scientific Affairs Board of the American Society of Microbiology and is a fellow of the American Academy of Microbiology. She's also a well-known member of the NSS and has been caving around the world. Many of us have seen some of the videos that she's produced, a lot on YouTube, and also an excellent video on caves in the Grand Canyon. If you have questions, please type them on your toolbar, and we will get to them. We're going to be stopping intermittently for questions. All of these webinars are always recorded, and they're stored on the NSS website of caves.org. You can view them later, or you can download them. We encourage people to use them for grottos, regionals, any kind of educational. They're there for you to use. I'm going to turn this over to Hazel now and let her go ahead and start the webinar. Hazel, you ready?
Yeah, I am. Thanks, Debbie. So thanks everyone for coming back for this. It's been about a month. Everything we know a lot more now, and so I thought it was time to maybe give an upgrade. Again, there. It's not really going to be. This really isn't going to be a cave talk. I'm going to talk about bats and the potential for spillback into bats and the danger to bats. But it's really not going to be a cave talk. It's really going to be basically trying to address some of the questions that people are bringing up on Facebook and questions they have. If you haven't seen the first webinar of one of these, I recommend you drop off, go look at that webinar and then come back and look at this one. I'm not going to do any kind of background introduction at this point. That was all in the first webinar. And I'm actually going to delve quite a bit more into the biology of this virus. So that's going to be some of the molecular biology. And that might sound kind of scary, but these viruses are basically pieces of genetic material wrapped up in proteins. Because of that, everything we really do is at the molecular level. So we just call that molecular biology. But hopefully you'll learn something and you get a better appreciation for virology. Just want to say where the information is coming from. So nothing that I present is going to be from the news media. Everything is either going to be direct from a reporting agency, something like the CDC. It's going to be from a peer-reviewed journal, and that means that it is science is being written up, the original data is being presented, the analysis and how the analysis done was presented, and it's being reviewed by other scientists who have judged it acceptable as research. And in addition to looking at the peer review journal, I'll actually also be looking at the quality of the researcher. So if someone has done a lot of work in this field, is considered a coronavirus expert, then we would consider their judgment much more informative than maybe somebody who's got no background and has just decided to leap into this arena. And then also the quality of the journal. A lot of journals have different levels of peer review, so the quality of the analysis of the work being presented is variable. So I've only really discussed things that I consider coming from quality researchers from quality journals. So there's not really going to be any opinion or any media stuff, only stuff that is actually being published. So I double checked everything I'm going to be presenting today to make sure that there was actually literature to back it up. So first thing I want to talk about is our update on our current understanding of the disease. So this was from 2 days ago. So worldwide total cases is over 3 million now, over 200,000 deaths. We have over 800,000 covered. There's actually a pretty good lag on this disease from the first signs and symptoms to when severe disease develops can be anything up to 10 days. And then people with severe disease can actually be in the ICU for up to 3 weeks. So there's a lag in recovery. It can take 6 weeks for people to be considered clear of the disease, depending on the testing methodology. And the other thing is that even though we're going to see the curve, we're starting to see the curve flatten and actually start to dip, we're going to see the death rate continue to rise because of that 2-week lag. So what we see in reduction in cases, we're not going to see necessarily in reduction of deaths for a while, at least a couple of weeks. We still recognize that the majority of infections are mild. So about 80% of infections don't require any form of hospitalization. Those that do require hospitalization, it's just under 5% of those patients end up in intensive care and in critical intensive care. The risk factors of ending up in the ICU include age. It's been the biggest one, over 60. Gender, men outnumber women about 2 to 1 in infections, and body mass index, so how heavy you are. And I didn't worry about that one until I got on the scales this morning and creeping into that territory. So I'm going to have to keep an eye on that. But a lot of the comorbidities that are associated with excess weight, including cardiovascular disease, diabetes, high blood pressure, those are comorbidities. So if you are older and heavier and male, you're much more likely to end up in intensive care than if you were a young, fit female. That doesn't mean that young people don't get the disease, and they may be important in spreading it around because they tend to be asymptomatic. So ending up in the intensive care unit, everybody's heard about respirators and how we're running out of respirators, and there's a desperate shortage of respirators. And all of a sudden, the need for respirators seems to have gone away. And that's because we're starting to get a better handle on actually the symptoms that this virus is causing. So as I said in my first talk, it is a cytokine storm. So it's an enormous immune response to the virus that is driving a lot of the symptoms, the severe symptoms. Younger people tend to have slightly more elastic lungs, so they respond better to the infection, and they also have a lot of immune suppressive proteins that we start to lose as we age, and those might help to keep the cytokine storm down. If you do end up in the intensive care unit, it's considered that you're suffering from SARS-CoV-2 acute respiratory distress syndrome. Of people that end up on a ventilator, so advanced respiratory support, essentially if you're on a ventilator, the mortality rate is about 65%. So if you are so sick that you need a ventilator, there's actually a pretty high mortality rate. And it's even worse for renal failure. The mortality rate is 90%. So if in addition to respiratory distress, you end up with renal failure, it does not look very good. And so I said that we think that maybe we don't need respirators, and there's some increasing evidence that we might be treating or have been treating the disease incorrectly. So we've been treating the disease as an acute respiratory distress syndrome, which means that we've been treating it as a pneumonia. But there's more evidence that it's like high altitude pulmonary edema. A lot of the signs and symptoms that we see in patients suffering from HAPE, so this high altitude pulmonary edema, and that's basically altitude sickness. There's 2 different kinds of altitude sickness you can get. One is on the brain and one is in your lungs, and HAPE is the form that's in your lungs, and strangely looks a lot like what we're seeing in patients with coronavirus infections. So this is a picture from a patient who has a pulmonary edema from high altitude sickness. And a pulmonary edema basically means that the lungs have started to fill up with fluid. So rather than an infection that's causing a pneumonia and you're having an immune response that's filling the lungs with with liquid, what's happening is the vessels that carry blood around your lungs are actually kind of getting leaky, and that fluid is pouring into the lungs, and that's what we call an edema, so fluid flowing in. And it's driven by a lack of oxygen and the body's response to it, but there's a couple of features that look a lot like ARDS or a lot like the coronavirus. One is that we see problems with movement of blood around the lungs. So pulmonary and peripheral venous constriction means it's basically where there's problems with blood flow around the lungs. And the other one is this capillary leakage that I said is causing fluid to pour into the lungs. The other symptom that's been associated with the coronavirus, COVID, are these disseminated intravenous coagulation. Basically in your veins and also in your arteries, people are starting to see these coagulations. So what's happened here is at some point in here, you've had an embolism. So an embolism is like a massive blood clot, and that is filled in the vein, and it stopped blood being able to flow back to the heart. So that's starting to fill up here. So this is a pretty severe form. You can see there's one here, there's some one here, and there's some stuff going on down here. And it's called disseminated intravascular coagulation because it's happening all over the body. And this seems to be a big sign. About 40% of patients who are coming in with COVID are displaying these symptoms. And in postmortem, in autopsy, some of these blood clots that they've been seeing have been reported to be the size of hot dogs. So these things are huge. So what's going on? Why are we getting this coagulation, and why are we getting this pulmonary edema? Well, I told you about the cytokine storm that brought in a bunch of blood cells called neutrophils, and there was an overreaction of neutrophils in the lungs in response to virus. And the higher the viral load you had, the higher the neutrophil response was, the higher this cytokine storm was, and you got this positive feedback. What's happening is that these neutrophils are releasing blood factors that actually promote clotting. And these blood factors will actually travel throughout the body. You get activation of fibrinogen, and you get fibrin deposition, you get platelet activation, and you get blood clots forming out in the arteries and the veins. And this is actually a common response of the body to an infection. If you've ever had an abscess is basically the body creating these kind of like blood clots to seal off the infection and trap it from the rest of the blood. And the reason we do that is that you don't want the bacterium, usually it's a bacterium, spreading around the blood. So what you do is you seal it off, you block it off with these blood clots, and you seal it off, and you try to fight the infection in place. But because of this cytokine storm, what's happening is all these effectors that are causing blood clotting are spreading all the way through the body. What we think is happening in the lungs is that these clots are breaking free. There are a lot of them form in the periphery and in the legs, and they'll break free. You get this embolism, which is basically a big blood clot, travels through the heart, and then it gets lodged in the lung. There's one here, some here, and then what happens is that every part of the lung that's being perfused beyond that is no longer receiving blood. Because it's no longer receiving blood, that tissue is getting damaged, and it's also not able to carry out oxygen exchange. So this is where this edema may be occurring. So it seems kind of scary that we're like, oh my God, we've been treating this completely wrong. We've been treating it like it's a pneumonia, but it actually might be this huge disseminated blood clotting all the way through the body. But it's actually good because we were putting people on respirators thinking that if we just forced more oxygen in, they'd be better. We have a lot of drugs and treatments for blood clotting. Everybody's probably heard of blood thinners to prevent heart attacks and strokes. And that's exactly what they are. And the idea is that these compounds can be used in association with drugs that will actually suppress this cytokine storm to reduce that blood clotting and actually help the patient. We have this So this is here, it'd be basically a healthy body. On this side, we have the severe infection, we have clotting, we have the production of these blood clots in the periphery. Material goes from there into the heart, it goes from there into the kidneys, and it goes from there into the liver. And so you can have damage in all of these tissues, and that's where that renal failure comes from. That's why we're seeing it. So if you have renal failure, you've got so much damage and so much clotting, it's actually spreading all around the body. So in a severe infection where you have a lot of this, you have these emboli, have them in the brain, they can be in the heart, they can be in the lungs, so you can have heart attacks and strokes. In mild infection, they just may be disseminated. You may have tingling or numbness in the extremities. But this is the interesting thing, is in 30% of people that were asymptomatic, that basically they had detectable virus, but they had no signs and symptoms. Up to 30% of them had blood markers for thrombosis. So even though they had no signs and symptoms, they were still actually having these effects in their system. Okay, Debbie?
Yep, so far so good.
Okay.
We do have a couple questions, if you got just a minute.
Mm-hmm.
How many different strains of the virus are currently known? Have any proven to be more infectious or more damaging to the pulmonary respiratory systems than this one?
So there are two strains. There's an L strain and an S strain. And the S strain was slightly more severe. It was found early on in the infection in China. That seems to have caused more severe disease and symptoms. That appears to have died out as a strain of the virus, and it's being replaced by the L strain, which causes less severe symptoms. So you get better spreading. Obviously, I think we mentioned it last webinar, as a foolish pathogen kills its host. So you really don't want to kill your host too quickly. What you want your host to do is survive and spread you around. So there's a lot of selection pressure to get less virulent, and it looks like we've actually seen a strain of that. So that S strain no longer is circulating, so we're down to just the one strain. And as I said before, it's a very stable coronavirus. It's actually one of the, if not the most stable coronavirus that we've seen to date.
Okay, let's see. That's the only one right for the moment.
Okay.
I'll
All right,
turn
well,
it back over to you.
So the big thing people are interested in is treatments, and you seem to see a lot of frustration with, what's taking you so long? Why haven't you guys figured out a way to treat this thing yet? And the important thing to remember is that we didn't know this thing existed until December 31st. We didn't know it was responsible for severe disease until early January. So we're really only about 3.5 months into understanding this infection. So even as far along as we are now is unparalleled in the history of science. And there will probably be lots of books about how the world mobilized. But, it's a scary time. We're worried about being sick. We're worried about being in hospital. So the question is what treatments do we have? First thing I want to do is talk about how we test viruses. So up to now, almost everything that we've done with this virus has been based just on detection. So we can use this technique called reverse transcription qPCR, and this detects pieces of the viral genome, the RNA that codes the genetic material for the virus. This test can detect it. So you can have a swab, you can stick that swab up someone's nose, you can rub it on a surface, you take that, you run it through this reaction, and we get something called a CT curve or a breakthrough curve. And what we're looking for is, when is the virus detectable? So a PCR reaction is basically a chain reaction, polymerase chain reaction. You have one piece of RNA that gets amplified in its first round to 2 pieces of DNA, and then those pieces of DNA get amplified again. Now you've got 4. So it's generally to the power 2. So for the first round, it's 2 to the 1, and then 2 to the 2, and then so on. So if you have 15 rounds of replication, you have 2 to the 15 copies, and that's detectable. If you're looking at patients who have severe coronavirus infection, we're actually seeing breakthrough curves. So we're starting to see copies of the virus as low as this 2 to the 14 cycles. Detection is considered good up to about 2 to the 30 cycles. So this is the window between a strong positive reaction and then maybe get on the edge of a negative reaction. I have seen with the white nose research people taking it way past 30, and then the data becomes noisy and unreliable. And it's hard if something's published and you don't have a background in this in the field. You might see it and like, oh, they've detected it, without understanding how important it is to get these assays to work. But the most important thing is this method can't detect viable virus. So what does viable virus mean? It means a particle of the virus that if it gets into your nose or into your throat will make you sick. The only thing that this can detect is copies of that RNA molecule, the genetic material in the virus. So if you had virus on this surface here, the virus died, its genetic material would still be left behind and it would be picked up by the swab. So there's lots of papers that have come out. There's been some discussion about how long the virus can survive on surfaces, how long it can survive in the air, what's the difference between cardboard and plastic. This was all done with this PCR technique. And so this is this threshold value that I was saying here. And you can see that some of these values are pretty high. They're going up to 31 and 35. So a lot of evidence was suggesting that this thing was sticking around between 1 to 3 days. There's new data that's coming out now that suggests that it might not stick around quite as long as that. And the reason that data has changed is they started looking for active virus. So now, rather than the pieces of the RNA, the genetic material in the environment, they're actually looking for live virus. And it takes a while to get to this stage because you actually have to do this with living tissue. The only, as I said, the viruses are metabolically inactive. They have no function and carry out no activity unless they get inside a cell. So the only way to study them in any way is to get them growing inside cells. So I just wanted to quickly talk about biological safety level and why that's just not being done quickly. So there are 4 levels of biological safety. Level 1 is a very environmental strain. So this would be like our cave lab in Akron. We're not wearing any lab coats. You can see somebody's got a soda out on the bench there. So it's BSL. You could drink these things. They're not going to make you sick. They're not adapted to humans, to making humans sick. BSL-2 is considered the next level up. So we have a lab that I use, which is a white nose lab. It's also a lab that we've done work on methicillin resistant Staphylococcus aureus, also known as MRSA. So these are labs that have negative air pressure. So air gets pulled back into the lab, so nothing escapes. You're wearing gloves, you're wearing lab coats. We'll wear shoe covers and hair nets when we're in there, but you take things a lot more carefully. So that's BSL-2. If you want to work on the coronavirus, because the coronavirus is an airborne respiratory disease that can cause death, you need to work in a BSL facility. So SARS-CoV-2 would be considered something to work in an environment like this. Tuberculosis is something else. So when I was a postdoc, I worked in a BSL-3 as on tuberculosis. These facilities are completely closed. They have environmental airflow that actually traps the air and captures it on HEPA filters. None of the liquids that go out of the lab untreated. So, you know, if you're flushing things down the sink, they're going to get treated before they're released into the municipal water. We used to have to shower and put scrubs on and cover ourselves and dress up basically like this before we stepped into the environment. And then when we left it, we'd have to shed everything and actually go through a decontaminating shower and then into a dressing room to get changed again. And this is BSL-3, and there aren't that many BSL-3 labs in the United States. There's probably about 29 of them. So there aren't that many places that are set up to actually be able to do this research to begin with. There is one level of BSL higher than this, which is the BSL-4, which is where you might work on Ebola, which is a contact contamination virus, and I'm not really going to talk about that, but those are the pictures that you might have seen in that movie, like Outbreak, you know, basically spacesuit kind of conditions. And then if you're going to be working on the virus, you've got to get cells to grow. And so you have to take the right kind of cells that the virus will grow in. You have to grow those cells, and then you have to infect them with virus. So these are healthy cells over here, and these are cells infected with the virus. And then when the virus grows and kills the cell, what it does is make things that we call plaques. So you can see where the virus, this is a stained area. You can see there's no virus here, and you can see the cells are being killed. So every time you want to do an experiment on this virus, if you want to look at active virus, you have to go through all these procedures. So we can do the RT-qPCR in my lab without any problems. It's pretty basic. It doesn't need a lot of controls, but you're not looking for that active virus. If you want to do the studies that help us identify vaccines and antiviral drugs, you have to have living virus to do that. And that's why these studies are difficult, time consuming and slow, is there's not many places to do it. It's technically challenging. And every cycle takes 3 or 4 days just to get the cells to grow to infect with the virus. So normally, these are the normal timelines that you might see with clinical testing. They've been talking a lot about clinical testing in the news, but normally preclinical testing is about a 10-year window. So that's where you would start with working in cultures of individual cells, and then you would move from the individual cells into a mouse. A ferret is a common model for influenza and also for the coronavirus. It has a respiratory tract that looks just like a human, the way it's structured. And then when you've worked in these models, then you would move up into the closest animal model for humans, which would be a rhesus monkey. And if everything looks safe and effective in those animal models, then you would move to phase 1, which is a small group of volunteers. It's an at-risk population, so it's people that might die if they don't get access to these drugs. If that has no effects, then you go to a larger group of volunteers, which would be a phase 2, which is usually hundreds of people, and again, an at-risk population. And then you go from there to phase 3, which is the general population. So these are people that aren't specifically in need of life-saving drugs or vaccines, and you need to recruit thousands of people for these studies. So you're looking at about a 20-year window for this to happen, and it's usually somewhere between a $200 million and $500 million investment to carry a drug or a vaccine all the way through the preclinical and into clinical testing. So when you see or when you hear in the news about phase 1, phase 2, phase 3 trials, they've already gone through preclinical and they're actually working in humans. The other thing you need to do is you need to control these clinical tests. And this is a lot of the issues that we've been seeing with the work that's been coming out of China. It's been done on very small groups, and they haven't been double blind. They've been single blind experiments. So they may have a cohort of 6 or 12 people that they're publishing data on. So it's a really small group of people that they're trying to make an analysis of. We call it a single blind placebo because you have 2 patients. One will have your drug and one will have a placebo. And what you're looking for is for that patient to claim they feel some effect, or you see that they're protected or they're getting better. And the reason that the patient is blind to whether they have the drug or the placebo is if they're not, then, if they know they've got the placebo, they're going to I feel worse, it's not working. Or if they think they've got the placebo and they actually have the drug and they see no effect, then there's no bias built in. But the problem is if the doctor who's giving the treatment knows, then that can actually lead to interpretation of the results that are biased by the doctor. So this gold standard is a double-blind placebo, where the doctor who's administering the treatment doesn't know who's got the drug and who's got the placebo, and neither does the patient. Only the person that is giving the treatment to the doctor knows that information. And so you may hear that people have been trying hydroxychloroquine, and we don't know, is it or isn't it? It's because the studies aren't being done properly. We need to make sure that they're done properly, because if you're going to expand this into the greater population, you have to do more good than harm. So if there's a 0.1% advantage for the general population and you expand that over 500 million people, that's great. But if it's a 0.1% reduction, you could be putting thousands of people's lives at risk. So that's why we take the time to do these studies. And that's why, you know, it might seem like, well, they said this, and then they said that it wasn't, and they weren't sure. It's because there's a certain standard that we'd like to see before we're confident that we're actually seeing results. You also need thousands of patients. As I said, some of these studies in China were pretty pretty tiny. And one of the more recent studies, I think the hydroxychloroquine study that was done in New York had several thousand patients. So you need large numbers to get statistical significant data. You okay, Debbie?
Yep. Okay, we do have a couple questions. First one, I read something about younger people with minimal symptoms having severe strokes, you just covered that, and testing positive for COVID-19. Is this caused by what you just were talking about with the clots throughout the body?
Yeah, probably. There's very, very few cases where somebody doesn't have a pre-existing condition. So they may have been young and apparently healthy, but there may have actually been a underlying condition that we don't know about. The other issue is how the immune response is activated. We don't know what triggers the cytokine storm. We don't know what if we knew what the triggers are, we could develop drugs and just knock it out in the very beginning. So you do have to be careful. You also have to be careful about anecdotes. Somebody, you know, there was a big study that showed that asthma wasn't a comorbidity. So basically, if you had asthma, you weren't more likely to get sick than if you weren't. And that was based on a study of 6,000 patients. And then as somebody on Facebook said to me, well, I know, you know, a friend of a friend's daughter's, you know, ex-boyfriend's son, you know, he had asthma and he got sick. But that doesn't negate a study of 6,000 people. That's an anecdote. So we have to be careful. Like we have to make sure the data we look at are these large groups of people. So even though there might be some intragroup variability, what we're looking at is the general pattern that we can extrapolate to everybody.
All right, the next one is kind of speculation. It says, what is the risk of COVID-19 vaccine having similar negative viral effects like the dengue vaccine?
I'm not familiar with the dengue vaccine study, so I can't comment on that. Vaccines go through a lot of clinical testing before they're rolled out, and they're very safe and they're very effective. Again, there can be some anecdotal, you know, stories of, you know, 1 or 2 people getting sick from vaccines, but it's very, very rare. And in general, the good they do far outweighs any possible side effects.
The next question is it really realistic that the Oxford group can get a vaccine ready for millions of doses by September of this year?
So I'm going to get to that. I'm going to cover vaccines in a minute.
Okay, so our next one is on an early chart, you showed approximately 3 million cases with about 1 million either recovered or died. Does that mean approximately 2 million currently still have active COVID-19?
Yes, there's some gaps because some patients that discharged from the hospital weren't tracked and who died weren't tracked. And there's some with people in nursing homes, we don't have great numbers on them yet. But yeah, right now there's about, well, we'll talk to that about how many actual active infections there are, but it's probably greatly exceeds 2 million at this point.
Okay. Would you speculate about the possibility and severity of the long-term lung damage that this virus causes?
Yeah, there's a lot of fibrin that is laid down, so there's a lot of scar tissue. There's also a lot of damage to the kidneys in people that who their kidneys are affected. And some of these people that are coming out of intensive care are very, very sick, and it might take them years to recover. So we won't have any of that kind of data. I mean, the longest surviving post-infection people that we have right now are about 3.5 months. So we aren't going to have that, but there's undoubted that there's going to have been a lot of damage to these people's lungs. The severity and how quickly they respond, we don't know yet. Okay,
All right,
so
next one.
okay.
Yeah, there's, believe it or not, there's still a couple more questions.
Okay.
It says there's reports of 6 strains in the last 4 weeks. What do you think the odds are that the virus will mutate into more virulent form in the southern hemisphere during this Australian winter? It
Okay,
says,
so
is it a safe assumption that there will be another mass infection cycle coming to the U.S. During the flu season?
yeah, so I'll get to that. I'll get to waves of
Okay.
infection. As far as 6 strains, I've not seen any evidence of that in the literature. There are individual mutations, single point mutations. It's a big genome. It's about 30,000 bases of information, which is very large for an RNA virus. And viruses mutate, their thing. But this virus actually has a proofreading enzyme that double checks the quality of the RNA it's making, much like our cells do. So the mutation rate is incredibly low. As I said, there's 2 possible strains of it that are circulating. I've not seen or heard any data to suggest that there are more than that. As far as whether it would mutate to become more virulent, no, selection pressure is for these to get less virulent. They really don't want to kill the host. They want the host to be able to spread them as far and wide as they can. So if the host gets too sick, so if we get too sick, we can't transmit it. Okay, so I'm going to talk about antivirals. So this is what everybody is being excited about. There was something in the news today about Remdesivir. I'm going to talk about antiviral drugs right now. So this is, as I said, I'll talk a little bit about the molecular biology of the virus. So this is, as I said, the structure of the virus. So this is the RNA. This is the protein, the envelope protein that allows it to escape from the cell that it's made in. And this is the spike protein. This is the S protein. So this is the really important protein. This is where immunity develops. And this is what is built inside the cell and released. And this is the genome of it. This is actually from a slightly older paper before CoV-2 emerged, but the information is the same. So there's 2 big domains. So this is the genome. This first half of it is considered non-structural proteins. So non-structure means that this thing that gets built, these proteins aren't involved in, and there's 16 proteins. The other proteins, which are the structural and accessory proteins, are things like the spike and the envelope and the matrix protein. So these are the things that actually build it. So these 16 proteins that are non-structural are really important in allowing the virus to hijack the cell and start making copies of itself. So what it does is it goes into the cell. The first thing it does is make a polymerase that will allow it to make copies of itself. So it allows the cell to make copies of the RNA into more RNA, which is something that cells can't do. And it has a helicase and a proofreading enzyme that makes sure that happens efficiently without any mistakes. There is a larger protein that is cleaved into lots of small proteins, and they fly around the cell and they turn down normal cell metabolism, they turn down normal cell protein synthesis, and they basically force that cell to become a slave to making copies of the virus. And these proteases, one of these is protease here, are really important because they help break down these bigger portions of the virus. So if you can actually knock out this protease, you can't activate any of the replication machinery. There's an interferon antagonist, so there's something that actually interferes with the cell's innate immunity and stops the cell from signaling other cells that it is infected. There's another protein that's involved in cleavage and activating of the structure of the virus, and then these replication proteins. Each of these is a target for an antiviral drug. So if you can knock out any of these non-structural proteins, you really affect the ability of the cell to make copies of the virus. And so you stop the cell from being turned into a slave, and basically you allow the cell to fight back. So Remdesivir is a nucleotide analog. So basically it fools this RNA-dependent RNA polymerase and inhibits it. And if you can't make this, you can't make the genetic material of the virus. You can't make new virus particles. You can't make new virus particles. The virus can't spread in the body. There are some protease inhibitors that we use in HIV. Some of those are being used to see how effective they might be against the SARS-CoV-2. This is another place that we can actually look for potential inhibitors of the virus, and this is viral entry. So last week I talked about how the virus is covered in a membrane. It's like a big bubble, and the cell it's attacking is also like a big bubble, and you kind of have to fuse the bubbles together. So the spike protein on the surface of the virus attaches to this ACE2 receptor on the surface of the cell. So it's kind of like, this is the lock and key. When I was drawing that lock and key mechanism, this is the lock and key. When this ACE2 is activated by binding of the virus, it does something called endocytosis. And basically what happens is it causes the membrane of the cell to wrap around the virus and pull the virus into the cell. Now, this endosome is designed to destroy the virus. And what the cell does is it actually will pump acid into this endosome. So it's basically made this tiny bubble in the cell that is surrounding the virus, and it's going to kill the virus by pumping in acid, and it also pumps in proteins to break down the protein of the virus. But it turns out that the S protein is actually activated by those protein cleaving agents and the acidification. And when you put it in the endosome and you hit it with the protease and you hit it with the acid, it actually activates the spike protein to force the membrane of the virus to fuse with the membrane of the endosome. So basically you bring those two bubbles together, and what it does is it shoots out the nucleic material into the cell, and you have an infection. Now, this is where hydroxychloroquine could have an effect, because it stops acidification of this endosome. And so if it works, what it's basically doing is stopping that drop in pH that would activate the protein and allow the virus to escape. But there's a second pathway. There's another protein receptor. It's a protease on the surface of our cells. It's called TMPRSS2, and it will actually co-bind. So if you have activation of binding of the virus, the S, to the ACE2 protein on the surface, the receptor on the surface, this protease will actually activate that spike protein and allow fusion directly of the virus to the cell membrane without having to be pulled in by an endosome. In which case, if it takes this pathway, you knock out the ability of the hydroxychloroquine to have any effect on the virus. So we don't know which pathway the virus takes. A lot of coronaviruses use both pathways. So even if you could knock out one, you might not knock out infection, because it might be able to take the second pathway. It doesn't mean that you might not be able to come up with a couple of drugs so you can actually knock out both of these pathways. And if we use HIV as an example, the best way that we've come up with of inhibiting viruses is to actually use multiple inhibitors. I think a normal HIV cocktail of drugs right now is 7 different methods of attacking the virus to stop it spreading. So right now for SARS-CoV-2, there are 700 drugs actively in development against the virus, and this includes 300 clinical trials. So these are trials that have actually got to phase 1 clinical trials and above. You may have heard of the hydroxychloroquine and the Remdesivir treatments that are ongoing right now. And so these are these double-blind studies. Some are saying there is effects, some are saying there aren't. But again, we need those high-quality studies to figure out if they're going to work. But this is the big take-home, and this is what people, I think, miss with this whole, everybody's getting really excited about this, and this is why I wouldn't put your money in the stock market right now. Antivirals have to be taken very early. If you start to show significant symptoms, it's too late. So you really need to have these antivirals in the first 1 to 4 days of infection. So if you're taking them because you've been admitted to the hospital because you're too sick to stay at home, it's too late. And so, you need to understand that antivirals, we don't have a great treatment against viruses. The best we have right now is against HIV, and that's because that's a very, very slow moving virus. It takes about 10 years from initial infection to death. If it takes you 2 weeks, you've got a really small window to get in there and have these antivirals work. So while there's a lot of excitement about them, you're going to need to be prescribed these by your doctor the first time you have a sore throat, and you're also going to have a test to show that you've got the COVID infection before you start taking them. So there's still some obstacles to overcome from these antivirals to being effective. Anything, Debbie?
Oh yeah, we've got several. If you're ready to take them, let's start with.
Sure.
Let's see. There's a recently released Remdesivir. I don't know how you say that.
Yeah, Remdesivir. Yeah, you got to kind of not say it like it's spelled, but yeah, Remdesivir. There should be an extra E in it to make it easier.
It says, is this data indicate meaningful efficacy?
So I haven't seen the data to make an informed opinion on it. I know that Tony Fauci today said that the data looked good. From my experience, he would not say that unless there was some good solid data to suggest that was the case. And this drug is actually developed for Ebola. So when we had the Ebola epidemic in 2016, there was a lot of money that the US spent in developing anti-Ebola drugs. And this was actually a failed Ebola drug, but they pulled it off the shelf because it was shown to have some efficacy in other coronaviruses. So yeah, it's interesting how Ebola is an RNA virus as well. So it was kind of interesting how they managed to find that and dig it out. And that's why we have a lot of these drugs that are in testing right now. It's because of MERS and SARS and the Ebola epidemic and influenza.
All right. Is it good idea to thin our blood if symptoms become severe, like taking aspirin?
So you need to talk to your doctor about that. I would not advise against taking any drugs without the advice of your doctor.
Here's one from Greg Moore that is on every NSS member's mind. Do you think treatments and vaccines will be along enough by next year to permit us to go to caving events?
I think so. I can't see us not being able to go to convention next year.
Do hot, steamy showers and deep breathing exercises help kill the virus in general?
No. Nor does breathing bleach.
Oh,
yeah. Kills lots of things. Oh, you included.
Well, this is by a deceased person named Floyd Collins. Let's see. There is some indication that the BCG tuberculosis vaccine may increase the body's immunological. This is really taxing my ability to say these words. Immunological reaction to other virus infections.
Yeah, there's some evidence against that. Some evidence of that. There's a lot of adjuvants that seem so. An adjuvant is something that stimulates the immune system. The only trouble is that the BCG vaccine is not given in many countries. It's questionable in its effectiveness against tuberculosis. So there aren't that many countries that use it. But there have been some data sets that I've seen that suggest that it actually stimulates immunity. And it could be involved in making, giving you a better immune response to the virus than that cytokine storm.
And this one says, what's the best estimate of the death range? Is it 0.2 to 1%?
We're probably not going to know that for probably 5 or 7 years. So there's a lot of data to collect because we've been undersampling. So yeah, it would be nice to say it's this. We have a range. I'm going to talk about that in a little bit.
Okay, and it says, what other drug studies besides Remdesivir?
Remdesivir, yeah.
Remdesivir, thank you, Remdesivir. Okay, have shown a decent p-value.
I think if you're interested in details of these studies, you should go to the World Health Organization, the WHO site, to look that up. It's a little bit more in depth than we have time to cover here.
All right, it says the first season of the Spanish flu, 1918, and its return with a vengeance in its second cycle of 1918 to 1919, and its third cycle, 1919 to 2000, to 1920, sorry, to where we are now, is that potential to mutate and become something equally infectious and deadly.
No, the virus, the waves that we saw with influenza were not due to mutation. It was just due to the population not have been exposed to it, and the big increase was from people returning from the war, bringing it back. I'm actually going to get to a lot of these questions in the. Okay, it's good. I think I like pre-planned this quite well with the questions.
Can antivirals be used to prevent an infection?
Yes, they can actually, prophylactically. So, you know, we don't know what the long-term effects of taking these drugs could be, but certainly if you're a healthcare provider and you're at risk and they're shown to be really helpful, then I can't imagine that they won't be used prophylactically.
And what will we look for in order to confirm or non-confirm that HAPE's treatments are effective for coronavirus infection, and when might we see such evidence?
So there's already evidence that this is starting to work now. There is some professors in New York. Obviously, New York is the epicenter, and a lot of this work is coming out of their studies. So I think they had a patient group of about 100 patients, and that they were showing that anti-blood clotting agents and immune suppressors such as steroids to suppress that cytokine storm actually dramatically increase the survival rate of patients. But you have to get to them before they get into the ICU. Once they're in the ICU, they're probably past that point. So every effort now is to prevent those people ending up on a ventilator. And it looks like, you know, the forced air and ventilation, if they weren't, I mean, if you were treating them as if they had pneumonia and they had this pulmonary edema, that's why there was no like benefit and outcome. You know, so many people were dying on ventilators is because you were giving them the wrong treatment. So there is evidence, data to support the idea that these treatments are actually a lot more effective. And, you know, last month, I think I said, you know, this flattening the curve gives us time to understand. And it seems scary, but this has been happening from day one, and we didn't know it. And now we know it. It's possible to manage those symptoms. So it's like every month there's going to be kind of an incremental increase in our understanding, and with that is going to become a reduction in mortality rate. Okay, so I'm going to go on. Yeah, I'll go on to immunity now. We'll see if we can cover some of these. So I just want to talk about immunity to the virus. So immunity that is learned, that your body learns to the virus, is mediated by antibodies. So antibodies, the structure of an antibody is kind of like a little Y like this. And there's a variable domain at the end that recognizes different particles. It recognizes foreign material in your body. And it's really fascinating how it does that. And it would take me an hour to explain how it recognizes it. If anybody wants me to do that, I can give you an immunology lecture to teach you how it does that. But what happens is that the antibodies do three things in the body. The first thing they do is they actually cover the receptors. So if you have receptors on the surface of the virus, if you have an antibody that recognizes it, the antibody covers that key. So that key can't fit in the lock. So that's called neutralizing. So you may have heard of neutralizing antibodies. So what they're doing is they're covering that virus so it can't get to its target. And it basically just floats around in the blood and does nothing. The other one is aggregation. And what happens is, because this is this Y and it has two binding sites, it can actually aggregate. It can actually start pulling. You can have another one here like this with another virus over here and so on. And you get these big aggregations. So when I try to explain how small these viruses are, if you have a grain of sugar and you look at a grain of sugar, now you imagine that grain of sugar is the size of a two-story house. These virus particles are going to be about the size of a grain of sugar next to that two-story house. So if you take a two-story house and shrink it down to the size of a grain of sugar, the virus would be shrunk that much from a grain of sugar. So they're pretty tiny. So they're hard for cells in the body to recognize. But if you make this big aggregation, this big particle, it's much easier for the cells in the body to recognize and attach to, and they'll actually consume this and destroy it. And there are tags on antibodies that promote this as well. And the third one is to block uncoating. So if it gets into the cell and it gets into that endosome, it's actually got to interact with the surface of the membrane and the proteins on the surface of the membrane and the proteases to be able to escape into the cytoplasm. And the antibodies can block that and stop that happening. And so when you have a vaccine and you get a component vaccine or a viral vaccine, you're making antibodies that do all of these functions in your blood, and that stops the virus infecting you. So that's why immunity is so important. It doesn't happen immediately. It usually takes about 4 days. So this is a week time scale along the bottom. So you first start to see antibodies in the blood at about 4 days. So there's two types. The one is called IgM, which is this huge big molecule here. And the other one is called IgG. IgG is going to give you that long-term response, and it's a memory response that allows quick clearing. IgG is what you want to come in early because you can see it's just like this big matrix, so it's really good at globbing things together. The window between when your antibodies start and when you're first exposed to the virus is when the innate system, so this is when those neutrophils and other cells are going to come in, and this is the cytokine, this storm event. So if you haven't started to build up and neutralize the virus with antibodies by about 1 week, this is where the zone of really severe symptoms can occur. But if you start to build a good antibody population, you'll actually clear the virus. So within 2 to 3 weeks, the virus will be cleared by the antibodies because you've made so many of them. And then you'll continue to circulate them. And these antibodies, they're actually memory cells that live in your blood. And some of these memory cells can live for 70, 80 years in your blood. And as soon as they see the virus again, there's no lag. You don't wait for a window for these things. You don't need an innate immune response. You immediately start making tons of this IgG that neutralizes it. So this is called neutralizing immunity. You can either get it from having the infection or you can get it from a vaccine. I'm going to say that's the neutralizing zone. When you have those neutralizing antibodies, you won't get sick when you're exposed to the virus. Now, there's a lot of discussion on whether we will get neutralizing antibodies against this coronavirus. And the reason I think that physicians and researchers have been reluctant to say yes is because we don't have the data yet. If you look at what we know about coronaviruses, these are all the coronaviruses, the human coronaviruses that are actually circulating out there right now. This one here causes croup. This one causes common cold. I kind of like this one because it came through a llama. This one here causes a common cold that came through cows. This one, there was only 2 patients that had this in 2005. SARS-CoV, which is the 2002 virus, and then the MERS-CoV, which is the 2012. And then, I'm sorry, I didn't look up this SADS, but it's unclear if there's a good transmission to humans. In every single one of these coronaviruses, we get immunity. So there's nothing to suggest that we won't also get immunity to SARS-CoV. So while we can't say explicitly that we have neutralizing immunity, there's no evidence that we don't. There were some studies that suggested maybe patients were getting reinfected because they were able to detect the virus again, but this was this RT-qPCR reaction. So it was just looking for the pieces of the genetic material. It wasn't looking for the active virus itself. So it doesn't look like there's anything to suggest that we won't be able to develop good immunity. And I think if we couldn't get good immunity, China would have been a really good test case for that, because we would have seen an awful lot more infections and they would have had a really hard time getting that under control. So immunity is really, this kind of neutralizing immunity is really important for herd immunity. So with no immunity in the community, where no one's ever seen this virus before, if you have a new virus come in, everybody is susceptible, and every person they come into contact with, they can infect. And you can see a large numbers of the population become infected. The only people who are protected are those people that haven't been exposed. And that's why social distancing has been really critical, is that it's limited those interactions and reduced the number of people that are getting sick. If you have people that have had the infection and recovered, or that they have had the vaccine and they can't get infected, it makes it hard for the virus to spread. So you can see in this group here, there are fewer infections. And then finally, when you get a herd immunity, which means that more people are infected, immune to the virus, when it's exposed to the population, no one gets sick, and as no one gets sick, they don't make more virus particles, and then they protect the rest of the population. I kind of like where people are like, there was somebody on Facebook a couple of weeks ago ranting about they never get the flu vaccine and they've never had the flu, and they think vaccines don't work. And it's like, it's because I go out and get my flu shot every year, as do about 70% of the US population that get the herd immunity that protected you from getting that infection. So this is why herd immunity is important. There is a level for herd immunity you have to reach to protect people this way. So protecting people that either haven't been exposed to the virus and recovered, or haven't been vaccinated. And those people, it depends on the virus. So for something like the measles, which is a really, really infectious virus, one about the worst we know, I think the R value for it is about 18. You need to get to 97% of the population has to have immunity to block the spread of that virus. And the reason we've been having these measles outbreaks in the US is because people are refusing to vaccinate, and we're dropping below those numbers, which is allowing it to spread. Something like influenza, which is much more like coronavirus, is about 70%. So those are the numbers that we have to get to. So that gets us onto vaccines, and somebody already asked about this. So vaccines are a way of giving an artificial immunity. So you don't actually have to have the virus and recover. You can give a component or a copy of the virus that won't make you sick, but still allows you to make those antibodies, allows you to make neutralizing antibodies so you can be protected. So there's, someone was saying there was a study at the University of Oxford at the Jenner Institute. I should point out that the Jenner Institute is one of the few institutes in the world that does vaccine research that's supported by a government. So it's not based on a pharmaceutical company and a profit model. And because of that, they've been developing vaccines to diseases that maybe there wasn't an emphasis to do. And one of those that they've been working on is a coronavirus vaccine. So they actually had a version of a coronavirus in, it was actually an engineered adenovirus. So adenoviruses cause sore throats. Most of us have had several in our lives. It's a very mild infection. This one is attenuated, which means that it won't even give you a sore throat. It will infect you, but won't make you sick. And what they've done is they've engineered the virus to actually produce the S protein of the coronavirus. So that adenovirus was given to 6 monkeys. They were allowed to develop immunity to that vaccine, and then they were infected with a very high level of SARS-CoV-2. And 28 days later, they're symptom and virus free. So it appears that there's protective, neutralizing immunity in these monkeys to the vaccine. Someone asked if this lab is able to scale to millions. They have been, the last I heard is they've reached out to companies worldwide, pharmaceutical companies worldwide, who are willing to work with them to make these millions of doses. On site, they can make 10,000 doses in I think they said 24 hours, which obviously isn't big enough for the billions that we would need. The only issue in the US is the US companies want exclusive worldwide rights, because this is non-profit. They're not willing to do that. So we may end up having to buy it from France or the UK. But it looks promising. They think that if the scalability they've got right now, because this is a virus and it makes copies of itself, so it can actually, you don't need to give much and it will actually replicate and make more copies of itself and increase your immunity in your body. You don't need a big dose of it. So it's a really good idea. And yeah, according to them, their scalability model could get them to, I think it was 6 million doses by September. And that might be scalable depending on what other partners they get, pharmaceutical companies. Right now, there are 107 active vaccine studies. That includes 25 different platforms. So that means 25 different ways of inducing immunity. 3 studies are in phase 2 and plus, and that plus is the University of Oxford study, which is actually going to go to 6,000 people, I think, beginning next month. And just to give you an idea of timescale, when we had the polio vaccine, it took 40 years to get the modern polio vaccine that we have right now. The fastest that we had, basically going from identification of so getting the gene, the genetic information of the virus to a usable vaccine for SARS, was 20 months. And if this Oxford University study works, we're going to get there in under 5 months, which even a fast vaccine is about 10 years. So this is absolutely remarkable, the amount of movement that we've worked towards this. And as I said, antivirals only work. They're not a magic bullet. They only work if you get them in the first few days of the infection. There aren't any really good treatments for viruses. So what you really want to do is you want to get immunity, and the way you get that is through vaccination. Okay.
Okay, well, we have a couple more questions. Let's see, get back to top. Okay, any thoughts about cases of reinfections that are likely mistaken positive tests?
Yeah, I mean, there's lots of complexity in how the people were tested, whether they were false positives. The RT-qPCR, we had some problems with it in the US when it got rolled out by the CDC, because so if you we make primers in our lab all the time, and you actually have to run them through a test to make sure that they don't fold on themselves. So these little pieces of DNA are like little pieces of Velcro, they're sticky Velcro that stick to the target. And you have to make sure that that Velcro doesn't stick to itself. And they never did the data analysis. Just, I have undergraduates doing this, but anyway, so it failed. So we don't have good testing records. There was a study that was done in Washington by an investigator who was working on influenza, and she actually did her own study. And we have some great data there. That's probably why it was first identified in Washington State, not because it was first there, but because that's where the first place they had a working test in the US. So there aren't a lot of false positives with that, unless they're not using the qPCR test very well, the breakthrough threshold. I was going to say, even someone who doesn't have a lot of viruses down at the 24 level. So it's, you're not getting down to those really, really low levels that maybe you might see with HIV. So I'm starting to babble here. It's again anecdotal, so there could be a couple of cases of that, but statistically not significant.
Okay, well, let's see. How is Pepcid, a GERT medication, possibly acting on COVID as a treatment?
I'm not familiar with that. I'm sorry.
Okay. Next one how would the BCG TB vaccine help provide resistance to COVID-19?
Oh, it activates components of the immune system that actually would drive the immune system towards antibody production.
And this one, I think I don't know if, Peter, if you want to restate this one. It says, what do symptomatic people have that others don't? I don't know if he means what do asymptomatic people have that others don't.
Oh, maybe the symptoms. So that would be, tiredness, a dry, persistent cough, fevers, chills. Just generally, if you have a persistent cough and you feel very tired, you'll have fevers. There's usually a 2 to 3 day fever window. The fevers can get quite high, about 104 degrees.
Another one is if you have the comorbid problem,
Comorbidity.
high blood pressure, etc., but it's under control by medication. Is this still a problem for negative impact by COVID-19?
Yeah, I mean, as long as we don't really understand enough about it, but if you have a risk factor under control, then it may not be as much of a risk factor if it was undiagnosed. But I wouldn't, that's definitely something you need to talk to your doctor about. I would just assume that if you have one of the comorbidities, that you think very, very carefully about your activities at this time.
The other one says, I've heard that quinine and zinc can be used as a natural alternative to taking a vaccine. Is this true?
No.
Okay, that sounds like it. Let's see. In 1918, Spanish flu cycle supposedly originated in the U.S. and spread from there. In theory, Missouri was reportedly widely disseminated. The first cycle didn't have a death rate close to the second and third cycle. Returning troops from France to provide active infection spread the vector. But do not explain the vast increase of death rates in 1918 to 1919 versus what happened in 1919 and 1920.
So I got that in a couple of slides, but it actually was debunked that it began in the U.S. It actually began circulating during the war in Europe. So we've got genetic profiling, which allows us to determine exactly its origin, and it looks like it was circulating as far back as 2014.
Okay, next one is can we not use the test methods developed by Germany and others?
We can. We should. That's a political question. I do not understand the complexities of that.
Okay, and Matt wants to know, what's your confidence level in, and I think you already answered this one, that we can go to caving events next year. What milestones should we look for that would possibly lead to that result?
Vaccine, and whether it's seasonal. So definitely the vaccine. I mean, the antivirals bias time. We can talk about, we'll talk about herd immunity and how many people really are sick.
That is the last question so far.
Okay, so
you blew through all those really fast.
Fantastic. So I just want to talk about, we're doing pretty well this time, the origin of SARS-CoV, and there's a lot of frustration among microbiologists that we're still talking about this, and I have to say I see something maybe 3 or 4 times a day on Facebook suggesting that this is an engineered virus that was deliberately released, and the I think it's quite hilarious actually is that in US people think it was a virus that was engineered in China and released, and in China the conspiracy theory is that this is a virus that was engineered in America and deliberately released into China. So it's pretty funny. There is no evidence that this is an engineered virus. I'm going to explain the data behind that, just so if people see this and people say I've heard it's engineered, you can push back and say no. So I just want to show you the structure of the virus again. I'm really going to focus on this part of the genome, which is the bit that makes that spike protein. So that's the receptor. So remember last presentation I gave, I said that you have a key and you have a lock and the key needs to fit in the lock, and it has to be a perfect fit for this whole thing to work. And that's the spike protein. The spike is the key, and the lock is that ACE2 receptor on the surface of cells. So the better the match you have between those two, the more likely that virus is going to stick. And you've got to remember this, you might be inhaling this thing and it's flying past cells at high speed. And so it needs to be able to stick, hold on, and actually get absorbed inside the cell. So this has to be a really, really tight interaction. So this is the genetic evidence that we have that this is not an engineered virus. So the first thing is that there are only a few scaffolds that you could build a coronavirus out of. And those scaffolds are things that you can actually, they're like building blocks that we have in culture that allow us to work on the coronavirus with the virus not actually being an active virus. So we can kind of imagine it's Legos, and we could work, you know, if the entire genome is 30 Legos in length, we work with 12 or 14, and it's pieces that get built up over time. Those pieces have a very specific genetic signature, and none of the SARS-CoV-2 has that genetic signature. So it's not built up of the building blocks that we could build this thing out of. The other is that there are two regions, we call them hypervariable, and that's where most of the change in the genetic information of the virus occurs. So this is SARS-CoV-2. This is the new one. It's this top one. And there's the closest bat strain that we have. There's the pangolin strain. There's the SARS-CoV. So this is SARS from 2003. And then there's a couple of similar bat species. There are 6 residues, so 6 pieces of amino acid in this protein. I'm going to mark them here. They're highlighted in blue. These are what form the key that fits into the lock. So if you have that lock and you have to have a very specific key fitting, there are 6 residues that do that, and these are these residues along here. They are different in SARS-CoV-2 in a very unusual way. And they're different in that there is if we were to design the perfect key to go in the lock, we wouldn't design it this way. There are a couple of changes that actually make this virus not work. So I think it's this one here and this one here would actually make the virus not work. It would actually be the wrong shape to go into a human cell. The only way you can make it work is if you have compensating mutations here. So that means that if you make these changes, it won't work unless you have a way of compensating for that change. And that compensation, you couldn't possibly guess at. There's no way that you could predict the molecular folding to do that. What you would do is you would use the ideal lock for the ideal key for that lock. You wouldn't make something that deliberately wouldn't fit and then come up with a compensating mutation. That would just be too difficult to do. Nature can do it. It probably means that this first change allowed it to hop into the animal host, and this compensating change is what allowed it to hop into the human host. So that's the first evidence. That's the first piece of evidence. Well, beyond that, it's not built from a known coronavirus. The other are these polybasic cleavage sites. So there's actually a zone here in the spike protein that allows it to be cleaved and actually increases the infectivity of it in human cells, and it's not found anywhere else. So basically you have a completely novel way of infecting that's never been seen before. And there's just no way that if you were designing a virus, you would put in something that you have absolutely no idea if it works. And it's compensated for by these glycan residues. So basically you put some sugars on it to make it work. So you've got an incredibly complicated system that no one would engineer, because no one would think to shove something extra in to make this work that's never been seen in nature before. So that's the other piece of evidence. So this is a really novel virus. It's never been seen before. This is basically a molecular comparison. So this is the receptor. The green is the receptor. So this is the lock. Pink is the key. This is if you designed the perfect key to fit in this lock. So you used a computer, you would actually build it this way. And there's a lot of changes here that have to be compensated for, and we couldn't do that genetically. The only way that can happen is it's gone through an animal many, many times. It's popped into a human, gone back into an animal, popped into human, and that's the intermediate host. This thing is deviated quite dramatically from bats. If you look at these residues, there were 5 that are involved in this binding pocket, and you can see it doesn't match any of the other SARS that we've seen, whether in the MERS or a civet. It's very different from bats. And when they create the ideal virus using a computer program, it's also very difficult from what you predict. So there's lots of evidence that this thing is completely natural and wasn't man-made. There's no signatures that the DNA has been cut and reassembled. It doesn't use components that we would use. And no one in their right mind would put in these weird mutations that strangely actually make this virus work better. So we thought, we don't know if there's a species barrier for COVID or SARS-CoV-2 into the human population, or whether it came straight from bats. But coronaviruses, the experts in the field, are increasingly saying there's no way this jumped directly from a bat, that there had to be an intermediate host. And with all the infections that we're seeing in cats, this may be some kind of feline that's allowed it to jump. So we talked about the possibility of backspill, that it could actually flow backwards from a human into the bat, and that's seeming increasingly less likely. I know they're doing the studies for that right now in bats to see if they can be infected with the virus, but I also know that they're using qPCR for those studies, so it'll be interesting to see what we get. Okay, we good?
Yep. Do you have time for some more questions?
Sure.
All right. Boy, we're just racking them up tonight. Okay. The 1914 flu circulation of Spanish flu references.
I would have to, if you want to go to Google Scholar and type that in, you should be able to find them. But there's they did some really interesting studies where they actually dug up people who had died and were in permafrost zones and were frozen, and they were actually able to pull the original viruses out of these people. So that's how they were able to come up with an evolutionary history of where these viruses came from.
Is there any data on what possibly the true infection percentage of the population is?
We won't have that for a very long time.
Because I keep hearing, I've read possibly that they're off by 85% or more, but
they could. Well, I'll get to that. Let's
okay.
jump. Should we jump into that right now?
Yep, sounds good to me.
Okay, so everybody keeps bringing up influenza from 1918, and it's the last time we ever saw something like this. And I think virologists and microbiologists, we kind of knew about this. We've all been lecturing about it, and it's kind of your typical case study in a pandemic. And we didn't realize we were in the middle of one until it was kind of like, whoa, we're really in the middle of one. And nobody had, even people that were specialists in the field, really didn't start taking this seriously until late February, early March. So the 1918 influenza had very close R naught values, so rates of spread and mortality rates, to what we're seeing with SARS-CoV-2. So it is a pretty good model. If you look at the waves of infection of this virus, this is about where we're at with the SARS-CoV-2 right now. So this is the first wave. We're still in that first wave. They had a really big second wave of that infection that actually caused a lot more deaths in the first wave. The things we have to remember is they didn't know what a virus was. They didn't understand immunity. They couldn't do any kind of testing. They didn't recognize the idea of asymptomatic transmission. So there's a lot of things that they didn't have access to, and tools that they didn't have access to that we do. And they also did not have the ability to design and build a vaccine. So if you look at that timeline, they had a year a lag between the first wave and the second wave. And by flattening the curve, what we've done, we've actually managed to kind of push those things back with social distancing. This is some modeling that just came out. This is looking at the impacts of different lengths of social distancing on the rates of infection. So the different colors correspond to different metrics that they use to build the model. You can see if you have a really small window of lockdown that we're in right now, the second wave occurs quite quickly, and the numbers are quite high. It would indicate that we're still kind of on the upward trend. The longer that you have this lockdown and this social isolation, the further you push it off. And this model is built on the idea that the coronavirus is seasonal. So if you actually have social distancing in place until late July, you might actually be able to push this second wave back into flu season next year, where we might have a vaccine. Again, there's no indication that we will, but there's also no indication that we won't. But we also know how to social distance at this point, so we do have a way of dealing with that situation. The only way of completely getting rid of that is that we all stay in our homes until this time next year, which obviously is not a reasonable expectation. So social distancing is not an exit strategy. It's how you flatten the curve and you buy time to come up with exit strategies. So how do we get out of this? So what we need to do is we need to get the transmission reduced. We need to increase our herd immunity, and we need to do contact tracing. We need to identify people who are infected quickly and get them into quarantine. This was the picture I showed last month. This is the R0. So if you have one person who is infected, what's the average number of people that they infect? We weren't quite sure where SARS-CoV was. We thought it was about 2.5 last month. This is the latest data. It's quite variable. So our R0 value is 1.5 to 3.5. I've heard people take it as high as 5.4. So this is really very infectious, much more infectious than we think. And it says very variable fatality rate. And this fatality rate is related to the amount of testing. So countries that have high levels of testing actually identify a lot of asymptomatic cases. So how do we reduce transmission? Well, we continue to do social distancing. When you're out in the park, stay 6 feet away from people. When you're in the grocery store, wear your mask, wear your gloves. And this is a really effective way of limiting transmission. A lot of people have been asking me about what to make masks out of. Surgical masks are pretty much the gold standard, but a cotton shirt, tight weave cotton shirt, 2 layers is going to give you about 70% protection. Dish towels actually wrapped around your face give you better protection, but it's really hard to breathe through them. So if you are wearing a mask you make yourself out of an old t-shirt that's not in too bad of shape, you reduce your likelihood of contracting the virus by 70%. And if that other person is also wearing a mask, then if one of you, even if one of you is infected, you reduce that transmission rate down to 1%. So if both people are wearing a mask, even if one person's infected, you've dropped the transmission rate by 99%. And that's because it appears that it's related to droplet transmission. It's not aerosolized. It can be in hospitals. It's a very unusual situation, primarily droplet transmitted. Just remember, if you're wearing this mask, if you have the virus, you're going to be breathing it into the mask, and the inside is going to be covered in virus. If you're out and about and you're using it properly and it's protecting you, the outside is going to be covered in virus. So don't take it off by grabbing the outside. Don't adjust it by grabbing the outside. Don't be playing around with it. Make sure it's a snug fit on your face. Basically, treat it like it's an infectious object when you get it back in the house. This virus doesn't appear to be long-term surviving on soft fabrics, so just wash it. So we have 3 in the house. We kind of throw them in the washing machine or hand wash them. Always remember to wash your hands, because if you're handling this thing and you do get virus on it, then you would get that virus on your hands. So you do have to continue to hand wash. The testing up to date has been primarily this qPCR, which can only detect the presence of the viral genome. So you actually have to have the virus there to be able to detect it. Serology allows you to detect whether you have antibodies to the virus, which means it can detect that you've been exposed to the virus weeks or even months later. So now we're starting to roll out serology testing. There's not a lot of it, but there have been some studies on asymptomatic people. So there have been some tests where they've taken random groups of people. There was a group of women in New York that were going to a hospital for to give birth, and their blood was taken. And after the fact, they went back in and looked at these people's blood for the presence of antibodies to the virus. And 14% of those patients, which were completely asymptomatic because they were coming in to give birth, had the virus. There was a study, a random study of volunteers in London that also found 14% infection. In Long Island, there was a study. It was a pretty large group. There's no information on how the people that were involved were collected. We don't know if they were healthcare professionals or they were people that were randomized. So it's still unclear what that group of people was. But 20% of those people who were completely asymptomatic had antibodies against the virus. And then there was a homeless shelter in New York. It had 400 people. They were all tested as part of a random study. Nobody in the shelter had any signs or symptoms, and 36% of the people had antibodies against the virus. So we think that there's a lot more asymptomatic infections where people have absolutely no signs or symptoms, or the signs and symptoms are so mild that they don't recognize it as an infection. A lot of times when you talk to these people afterwards and you ask them, how about this and how, and they're like, well, I didn't feel so well one day and my stomach was upset. That might have been when they had the virus. Because of these numbers, these are looking at people that would have no reason to think that they had the infection because they had no symptoms. If we extrapolate this number to the US population, it means the actual numbers of infections in the US right now is between 52 and 133 million. So it's obviously much more important to be wearing that protective gear to protect yourself. But it's really important in herd immunity, because if 133 million people have been infected and recovered and have antibodies that are neutralizing against the virus, it means that they're protecting us from the spread of it. We aren't going to know those numbers for a while. We have to get much, much better testing online, and we have to do much better contact tracing. And contact tracing is going to be the key, and this seems to be the one that riles the most people up. This is a map of infections in Singapore. So each of the next side, at the middle is an infected person. So this person here infected a group of 45 people at a conference. And then this zone around the outside are the people that they infected. And then this zone here are the people that these people infected. So you can see that one person infected hundreds of people. One person they infected went over here and infected hundreds of people, and so on. And what happens is when one person is infected, you identify that person and you test every contact they came in with. So these are early cases early on where people didn't realize they had the virus, infected a lot of people. But each of these dots where you see, singles, that means somebody was infected, was identified before they actually started shedding virus and spreading it to other people. So they were able to identify those people and get them into quarantine before they could infect other individuals. So you can see if you can do that contact tracing and identify people quickly and get them in home for 2 weeks, you can dramatically drop the infection rate. I believe South Korea does this. They have a phone app right now. And I think for the last 2 days, they haven't had a single case of coronavirus. This is current testing in the US, which looks pretty impressive. This is 5 million tests. We actually started very, very late. We had the capacity to start in here, but we started much later than that. And it looks impressive when you say we have 5 million tests, but the US actually lags far behind the rest of the world in per capita testing. And if we're going to do that contact tracing, we need to be doing something on the order of 5 million tests a day, as opposed to 5 million tests cumulative. Now, this is the thing, like I said, that gets people riled up, because the way that we can trace contacts is through our phones. So if someone has an app, this is the Korean model. You have somebody in a home, person A, they get on a train, they go to work, they come home, they've interacted with the person they live with, they've interacted with these people on the train, they've interacted with these people closely at work, these people far away, and then they've gone back home. They wake up the next morning with a fever, They go to the doctor because they can have a drive-through test that gives them the results in 5 minutes, and it turns out they're positive for the virus. They hit a signal on their phone, and the app sends out data to every person that that phone came in close contact with. All of those people are quarantined at home. Everything that they've come in contact with is decontaminated. And then the people that came within a social distance are advised to keep checking their temperature and make sure they have no signs and symptoms. And South Korea used this model, and they never closed anything down. They actually kept going. And they were super aggressive. Now they had apps that actually identified people, and there are ways of doing this anonymously. But every time I brought this up with anyone, even with my sister, she was aghast that she could possibly be tracked through her phone, even though Facebook and Google are doing it on a minute by minute basis. But that's a political question, and I'm not going to get into it. So just got one last slide, and this is really like there's a lot of confusion because you're having science content taken by the media and interpreted and pushed out. So there's a big disconnect between you and the scientist that's being interpreted by somebody in the media who doesn't necessarily have a degree or a background in science. And it doesn't mean that they're not trying. It's just that intricacy, like, reading the paper and then say, well, they use qPCR and their breakthrough curve was 32. This is not that great of a study. That's going to be lost on them. And so it seems like we say one thing and then we change our minds, and there's a lot of confusing data out of there, and it's like, why can't you decide? And the reason for that is it's the fallacy of the 100% proposition, the idea that when a scientist says something, that is it, that it is true, that's it, it's in concrete, we've made a decision, this is what it is. But the reality is that science is based on interpreting our current evidence and understanding. And every day we're learning something new, like, the HAPE versus the treating with ARDS. That's like a major breakthrough in treatment. And if we hadn't learned and we hadn't changed our minds and we hadn't argued and discussed and thought about the best way that we should move forward, we would never have gotten there. So it seems like we're arguing, we can't agree, and somebody says this and somebody says that. It's all about the quality of the data and how it's presented and how it's interpreted, and then how experts in the field look at that information and say, well, this study had these errors, why don't we try it this way? It's iterative. So it's always going to be changing. It's always going to be dynamic. Always feel that you can reach out to a scientist. Most of you probably know professors or biologists. Feel free to email me. I do what I can on Facebook, but sometimes I'm just too depressed to answer another question about whether this virus was genetically engineered. But feel free to ask. It's a scary time. I'm not scared because I understand the biology, and I see a lot of hope, and I see a lot of forward progress. I mean, the thing in Oxford is great. It's probably, it might be the first vaccine. There might be 12 different iterations of the vaccine. We get neutralizing antibodies against these coronaviruses, but we do have to have boosters. It seems to wane after a couple of years for reasons that we don't know. Maybe we can come up with a vaccine that doesn't need a booster. So there's lots of questions that remain and things that we need to work on. So I'm just going to leave it with the same slide from last time. Books I recommend, podcasts, Vincent's This Week in Microbiology and This Week in Virology. If you really want to get into some technical stuff, he does one called Immune, which is just about immunity. And then, actually, I changed the slide here. I teach a couple of courses in microbiology. I think I was promoting my courses, but that's me. That's my presentation.
Okay, great. We do have a couple of questions. Let's see. Guesstimates on whether there will be a second surge if we actually relax the social interactions within the next month or so.
Mm-hmm. Yeah, there's no doubt there will be a second surge. When it occurs and how big it is, we don't know. We need to continue wearing our masks. We need to continue social distancing. It needs to be very carefully rolled out. The way we do it is through testing and contact tracing. I mean, we could put this thing away in 6 weeks if we could test 5 million people a day and have everybody tracked on their cell phones. It would be gone in 6 weeks. but there's political ramifications of that. There needs to be massive investment. Every microbiology in the lab in the country needs to be shifted towards making tests and testing samples. So there's lots of there needs to be change. There will be a surge. The important thing is to not panic when there's a second surge, a second wave. It's going to come. We just don't know how big it's going to be.
Okay. Let's see. Can we learn about antibody levels needed to get immunity for determining usefulness of antibody testing?
Usually if you've been exposed to the virus and you've recovered, you will have high enough levels in your blood. There are actually controls that you can do. So there are low antibody negatives and low antibody positives, and those are actually built into the test when it's done. Ideally, what we'd like to do is come up with a test that's kind of an antigen test that actually looks for active virus in your nose, where you could actually stick this thing up your nose, wiggle it around, and much like a pregnancy test, it actually looks for the structure of the virus itself, and it might tell you in 2 minutes if you're infected. So there are lots of ways forward that we'd like to do that, but we definitely, I think I said this before, and I'm always going to keep saying this until it happens, is the way out of this is through testing.
Let's see. Can you explain to us how to use gloves properly? That's another thing that I've seen many people wearing gloves, but they don't know how to take them off, and I keep referring them to some of the medical videos on YouTube on how to safely take their gloves off.
Yeah, it's you got to peel them. So I'm gonna try and visualize it here. So the way I do it, the way I do it is if I've got my fingers in my left hand, I grab the palm of my right hand and kind of cup the cuff, and I can grab the cuff and pull it forward and actually peel the glove off my right hand. So it's kind of inside out, partially over the glove of my left hand. And then that allows me to slide that glove over the left hand and pull that off. So they end up being inside out. And then I have 2 sets, and I just wear them alternately in the car. When I'm out and about, I just leave them in the car on the seat because the virus doesn't live that long on soft surfaces. So I wear one pair one day and the other pair the next day. I'm not worried about the virus getting on the seat and getting contaminated that way because I'm not sitting on the seat. And I just interchange them every other day. I don't go out that often, so I'm not really needing to use them, but yes, that's how I do it. It would be great if you had medical gloves, because basically I use medical gloves at work all the time. That's how I take the medical gloves off when I'm working with pathogens. But it gets to be a habit where you can do that. But yeah, it's the trick of trying to hook it on the cuff of one hand with the other, and you basically fold them in on themselves. So the side that would have been exposed to the virus is now tucked inside.
Now, you were saying laying it on the seat because soft surface of virus doesn't live that long. Then our masks, we're wearing the cloth masks. Can we, if you use your mask when you're driving, can you have a safe place to set it and then use it when you get back in the car the next day or the day after? Or should you wash the mask every
I wash mine because it's got snot and boogers on it, and it's picking up droplets, so it's a little bit grosser than gloves, which is why I washed mine. I do have a couple hanging from the rearview mirror in case I forget to take my cloth one with me. But if you need to, but it's kind of gross. The other thing is we don't know what the dose is in a droplet, and we don't know what the effect of the mucus could be. So I would recommend washing it.
Okay, let's see. I see people wearing masks, but should they also be wearing glasses if the droplets get in their eye? So if someone coughs in your face, of course you're in trouble. But they want to know if we should be wearing eye protection as we're walking through stores.
So there are some people that do. I think if you cannot control the urge to touch your face, you probably should. If someone's coughing, you're going to avoid them. They're not going to get to the point where they can cough in your eyes. But if you are unable to train yourself, and it's so reflexive. I mean, yeah, even like Tony Fauci's been doing it on the TV. It's hard to be like, don't do this. And I must admit, I do it every now and again. That just rub my nose on my eye. But yeah, if you find yourself unable to stop reflexively doing it, just wear some goggles.
Any statistics on people that were sick, recovered, and then showed that they were reinfected?
No, there's been some anecdotal evidence that a couple of people have mentioned that that was all done by qPCR, so we don't know if they were shedding active virus. They would need to be shedding active virus, and that was not done. So there's some anecdotal stuff, but I think if that was the case, that you didn't get immunity against this virus, it would be a first for the coronaviruses, and you'd have seen a very, very different epidemic in China.
Half-face respirators, efficacy with PM100 and organic vapor cartridge. Do you know anything about that?
I mean, if you've got something like as a full face respirator, that's going to give you better coverage than a cloth face mask.
Singapore infection surge is being now attributed to migrant workers, close quarter housing, etc. Do you have any info on that?
Yeah, China's been seeing almost all of the infections that they're getting in China now are people actually coming into China and bringing it with them. So it's not really, it's going to continue to be a problem until numbers are brought down. I think I have friends that live in New Zealand, and they've completely shut down all tourism in New Zealand, but they don't have any cases of it in the country right now. I'm sure if they have people coming in, then you might see them bringing cases with them.
Antibody plasma collection, enough to treat all those that are sick in the future.
Yeah, so that's actually, I didn't touch on that. So plasma collection is basically if you've recovered, you have those antibodies that could protect someone. And those do work. If somebody's very sick, you can give those to someone. So unlike the antivirals that you have to get very early on, you can give that plasma to somebody who's very sick, and it's very useful. It's a very labor intensive and incredibly expensive way of doing it. I think I heard somewhere that they would charge $5,000 a treatment if they did that. Yeah, so it is a band-aid for the sickest people, and if you know that you've had it, you've recovered, and there is a system in your state for plasma donation, I strongly encourage you to look into it.
Now, do we have any statistics or know for sure if this is going to be seasonal? Now, I've heard that it's going to end up being like our regular flu season. It's just going to be sticking around forever. What are your thoughts on that?
Yeah, we don't know if it's going to be seasonal. We still don't. I mean, half the people think it is, half the people think it's not. It's too early to tell. The thing about cold viruses, there's only 2 circulating forms of coronavirus that cause colds, but they cause 30% of the common cold, and we've all had them multiple times. And so this is the only thing about coronaviruses. So the influenza virus can go through this genetic shuffling to escape our immune system, and it can also go through something called drift, where it changes enough that it's not recognized in a few years. The coronavirus doesn't do that. It's a really stable virus, but for some reason, our immunity against it does tend to wane, which is why we can get another cold. The thought is that, the most severe form of the virus you might get is the first round, and then subsequent infections, because you'll have some level of immunity, will look a lot more like just a common cold. And the more of those colds you get, the more of a boost you get. So we're not quite sure what the future is going to look like. Worst case scenario is that you might need to get boosters every year, the same way that you get an influenza booster. And you should be getting the influenza, you should be getting the flu vaccine anyway. It's really important to protect the young and the elderly to have that vaccine. So they might just make a cocktail where they mix the 2 of them together. And it would be good, actually, because I think, people will be a lot more afraid of contracting SARS than they have influenza, even though influenza is quite dangerous. So it would be good, actually, to get the herd immunity up against influenza.
As you're wearing 2 layers of gloves? Is that 2 layers of cloth gloves or 2 layers of medical gloves?
I just wear my running gloves. I
But you
don't
said
think
you wore 2 layers, right? One over the top.
that's for the mask, cotton mask for your face.
Oh, okay, I thought you said you were wearing 2 layers of gloves also. Okay.
No,
Um,
that's what I fold. I've got one on each hand, but I kind of fold it in on itself when I'm taking them off. That's what creates the layer on top of layer.
okay, 60 plus age, 60 or above. Do you have recommendations for staying safe that may be different from what the CDC says?
No, I would definitely follow CDC guidelines. If you can avoid going out as much as possible, that's good. Avoid interactions. My parents are in, they have several comorbidities. So my sister, they still live in the UK. My sister actually leaves groceries for them at the doorstep and then waves to them from the driveway. But, they have several factors beyond age, counting against them. I think, the as much as you can, you know, avoid, when you go grocery shopping, shop enough for 3 weeks, don't go every 2 days. I've gotten much better. I used to go shopping every couple of days and go buy grapes, but I've gotten a lot better about pre-planning and trying to avoid going out as much as I possibly can, have deliveries to the house of things rather than going to shops. So anything you can do, but at the same time, think about your mental well-being. I'm going kind of stir crazy, stir crazy here. I get all
Exactly.
excited when the postman comes and I get to walk down to the mailbox. So,
Um, Here's a question I've heard people many times and I've read about it. It says, should I be concerned about bringing groceries into our homes without cleaning them? And I read recently an FDA statement that said we don't need to do that. What is
yeah, I
the
think
scientific?
it's unlikely that enough of it sticks around and survives long enough. I'm going to say that's the difference between doing these qPCR tests and looking for active virus. So it's if someone like sneezes in their hand and wipes it on your grocery bag, then yeah, for sure. Some people I know take their groceries, leave in the back of the car for 3 hours and then go get them later. So whatever makes you feel comfortable, but I think it's important. Somebody was asking me about whether they should try to sterilize the sliced meat at the grocery store when they got it home, but I pointed out that they actually have sterile techniques and high levels of hygiene, because otherwise you'd get food poisoning from the meat. So it's
Mm-hmm.
it's an unseen thing for me. I'm probably the world's dirtiest microbiologist, because I have a fairly reasonable comfort level with what the risk factors are, but I think you should do what you feel comfortable with. If you're very concerned, you can leave it in the back of the car for a few hours and it should be okay.
Unless it's perishables. Uh,
Yeah. If you got ice cream, maybe you want to take some ice packs or something, or maybe not buy ice cream for a while. Yeah.
okay, is it worth getting the quadrivalent flu vaccine versus the most common vaccine?
I'm not familiar with that. I'm sorry.
And it looks like quadrivalent versus trivalent vaccine.
Yeah, I'm
So
not
four.
familiar. Yeah.
Okay. I'm going. Let's see. I'm going out with half face respirator and gloves. Now that Delaware requires masks for all public. So much for feeling safer.
Yeah, I mean, you will be safer as long as you wear the mask properly and make sure it fits well. There's lots of evidence that this works. I remember a friend of mine said that we'd never wear masks because we're not a mask wearing society, and my response was yet. So, we
Yep.
might be wearing these for years, and you might feel comfortable wearing one when you start walking around airports again. So, things are going to change. We aren't going to know quite how the world has changed for a while yet, but we have a lot of knowledge and we have a lot of technology and a lot of skills that we didn't have in 1918. So I think we're in a much better place. I don't think that the worst case scenarios that we imagine we could be having. We don't know that we're going to have a vaccine in September. We don't know that we're going to have a vaccine next year, but if we certainly have the capability and technology to get there faster than we ever have in the history of humanity. And we made it through the 1918 pandemic, and we'll make it through this one.
What is the temperature variance for the survival of this virus?
Oh, so I don't know the specific numbers. I know that's been published. So usually, 60 degrees centigrade, something like that is gonna kill this thing off. So summer, if it's a regular coronavirus, it probably won't do as well in the summer. Drier, warmer air, more sunlight is usually all negative for it. But I know that those analyses have been done. I just don't know those data.
What about the cold? Max wants to know if refrigeration or cold will harm the virus.
So refrigeration will actually probably protect it a little bit because it slows the degradation down, but freezing will damage the membrane. But I would not, I'd stick with chemical disinfection rather than, and if there's a very specific reason why you would need to try freezing, I would say stick with the chemical disinfection.
Well, I think that what they're wondering about is maybe putting, food containers or something in their fridge that haven't been cleaned or
yeah, I mean,
like
you should be okay. I mean, you should be okay. I mean, there's like a level of risk, and you can be overly paranoid. I don't want to like say it's fine and there's no danger because I don't know, right? I have no idea what the chain of custody is between when that thing was manufactured, who manufactured it, and when it ended up in your fridge. But we should be careful but not afraid.
Someone says for those that are unscientific, that are non-scientific savvy, 60 degrees centigrade is what?
Oh, hey Siri, what is 60 degrees centigrade in Fahrenheit?
You're kidding me.
60 degrees Celsius is 140 degrees Fahrenheit.
140 degrees Fahrenheit.
Oh, what would you do without somebody listening to your eavesdropping into your conversations? I tell you.
Yes, the Russians are writing this all down right now.
Yeah, right now. Can the virus live in a cave if an infected person goes in there and leaves it?
I doubt it. There's no reason to think that it would survive any better in a cave than anywhere else. In fact, I imagine it'd do worse because the surfaces are calcium carbonate is a charged surface that will stick the virus. So I imagine that there's no higher risk in a cave than there is in any other environment.
Any advice for a 90-year-old mom? I know my 86-year-old mom, it's like she hasn't left her house in 7 weeks. She lives near Seattle.
Yeah,
that's the best advice we give her.
My mom's been doing a lot of gardening. Best advice is maintain and manage your social networks. Get some media on your computer that lets you reach out and talk to people, stay in contact with your family. Make sure you reach out for help if you need help with groceries and getting things to the house, but you really should avoid going out as much as possible.
Now here's one I've heard the opposite. It says the CDC suggests warm and humid conditions sustain the virus longer than dry, cool environments. Is it expected that dry, warm environments are more harmful than wet? Now, I read an article by a virologist who said he's in Puerto Rico, and he said it's so hot and humid down there that nothing can survive.
Yeah. It would be nice. Unfortunately, not. No. Yeah, I know that the people have started looking into this. There's some evidence that maybe humidity supports the virus a little bit more, but it's in droplet form. It drops out of the air. So, aerosols are very specific. They're only formed in really specific ways. And most of the time when you intubate a patient in hospital, so you put them on a respirator, that's going to create those aerosols that hang around in the air for long periods of time. So the droplets are dropping out of the air quite quickly, which is why the 6 feet of social distancing works, because they don't really make it that far. there's a lot that we're going to understand how this virus responds to heat and temperature and humidity versus dry conditions as we go into the summer, and we see whether we have a seasonal coronavirus or not.
Okay. And Mark, with a 90-year-old mother, says that she has lots of doctor's appointments, has to leave the house. Any suggestions?
Yeah, if she can do those doctor's appointments remotely, most
Yes.
doctors are set up for that, especially if she's in a high-risk group. She really should be trying to do those remotely. And I know most states have relaxed the rules that allow that to happen now.
All right, and that is
I hope
that is
so.
our
I
last
hope that's
question
it. Getting tired.
That is the last question for the night. Everybody says, thank you so much. You've done a great presentation. Thank you for your time. And I have to tell you, we had such a huge amount of people that watched your video last time. Like, I think, was it your husband saying that your video went viral?
Oh no, it didn't. It didn't quite go viral. It was like it was quite a few people. I was surprised. It was great.
Well, we were kind of laughing at the webinar on viruses went viral. So anyway,
Yeah.
Thank you very much. We greatly appreciate it. We're really, really privileged to have you here, and that you would take your time, because I know you got to be swamped, but you take your time to put these PowerPoints together, and they're always so amazing. I've got so many emails and texts on people saying that you take such a difficult, unbelievably complex subject and make it to where the typical carer can understand them. It is stunning.
I think your typical caver is above average on curiosity, and I think that's all it takes really. And I hope this was a much higher level one than the last one, because I'm assuming people watched the last one. So, I don't think I'll take it much higher than this, but there's certainly a lot more information online. If you go to a curated site like Google Scholar, and make sure that whatever it is you read, that lots of people have referenced it to show that it has value, then you can definitely delve into this as deeply as you want. It's microbiology is
and
really cool.
Then don't allow Facebook to be your guide, please, people.
Yes, no, there's a lot of crap on Facebook.
I mean, it's so frustrating to see the craziness that goes on there, and people take it as gospel. Like, that's why Hazel's doing this, people, is because Facebook is not really accurate. So, well, thank you very much. Any parting words before we close up for the night?
Thanks to whoever stayed to the bitter end. That's great. I appreciate it. Thanks for being interested.
Everybody, we've had almost no one drop off. And your webinars are one of the few that we don't have people leave partway through or leave when question and answers come up, because they're like, well, I don't want to listen to question and answers. They just stay here. You have the highest retention rate ever of any of our webinars.
Wow, that's cool. Well, if anyone has a question and they didn't ask you, or there's no such thing as a stupid question, just stupid answers, right? And hopefully I won't give any of those. Just go ahead and email me, hazel@cavescience.com.
Now, I also want to thank all of the healthcare workers that are out there, and all the scientists and researchers that are spending all the time and effort and sacrificing so much. We have several of our NSS members that are nurses, doctors, PAs, etc., that are literally sacrificing every minute of their time and time with their families to help with all of the craziness going on and protecting people and caring for them. And I want to thank all of those people. There is no way our society would be where we are if it wasn't for the sacrifice people like you and others that are grabbing this virus by the throat and trying to shake it and make it give up. So thank you very much.
Thanks, Debbie. And thanks to everybody.
All right, everybody, have a good night. Thank you for showing up. As usual, this is recorded and stored on the NSS website of caves.org. It's also on YouTube. The NSS has its own channel. please share this with people. The more people you share it with, the more lives that can be saved. We just need to really get this true information out to people, and it's fact versus fiction. And this is a fact, and there's too much fiction out there. So everybody cave safely. Until next time we meet, have a good night.